Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. Today we're going to talk about the sustainable energy cycle and how we can generate and store power through electrochemical processes. My guest today is Dr. Hadi Tavassol. Dr. Tavassol is an Assistant Professor of Chemistry. Welcome, Hadi, and thank you for joining us on Talking Points.
Thank you for having me.
Well, let's talk about energy in general from the big picture perspective. We know that reports have come out in recent months that because of the improvements in the technology for fracking and slant drilling and so forth, we're actually producing oil in America at the clip of about 10 million barrels per day, which takes us right back to 1970 at the peak of oil production. And people are saying today, well, with so much abundant energy and America is actually becoming very energy sufficient now, why do we need to worry about all of these alternative technologies?
Yes, so that is a good question. So the problem with the fossil fuels, that we are actually at the peak of the production now, as you mentioned, back to levels that we haven't seen for a very long time, is the CO2 emissions, or what we call greenhouse emissions. And the side effect of that is really changes that we are going to do to the planet. We measure the concentration of the CO2 in the atmosphere, and we are now in the level of 410 ppm, part per million. If we include all greenhouse gases, we are around 490 ppm levels of CO2 emissions. That means that we are looking at temperature changes of the Earth from pre-industrial time that up to now they're around 1 degree Celsius. And we're really looking at 2 degrees Celsius temperature increase if we continue as the way we're going, actually.
All right, well, let me just stop you there for a second. So we're talking about a carbon footprint that we're generating with all of these hydrocarbons that are a byproduct of utilizing fossil fuels. People say, well, you know, the economy's going really well right now and we have all this oil production. Can't we ease into this more gradually so that we don't disrupt the economy?
Yes.
What you're telling me is that time is short.
So that is exactly true. So what we have so far is that the increase in the temperature, which is, as I mentioned, 1 degree Celsius so far. And as with the way we are going, we are looking at 2 degrees Celsius increase in temperature. That's going to have a lot of effects on the way that we do things in this planet. So let me just summarize a little bit of what's happening here in terms of CO2 emissions. So there are a few things that are the source of the CO2 emissions. The main of one of them is fossil fuel. It's actually 65% of it comes from fossil fuels. Less of it is land use, agriculture. So from this 65%, there are different sectors that contribute to it. For example, electricity production accounts for almost 30% of it. Transportation accounts for another almost 30% of it, these CO2 emissions. Now, what we've done is, beginning from 1970, really, we started seeing this spike in the temperature. After that, it was really within the noise. So we started noticing that the temperature of the planet is going up. And from 1970 to up till today, we have seen 1 degree Celsius warming. And if we continue the way we are going, and even we cap everything, we do not increase any fossil fuel consumption, we are going to see 2 degrees Celsius probably within a few decades.
And that's pretty devastating from what I understand from our previous conversation about this. And I know that we're now into a period which scientists are referring to as the 6th mass extinction event. Yeah. We've had 5 mass extinction events before. Let me just reference the 5th mass extinction event, which happened about 66 million years ago.
Yes.
That's the event that wiped out the dinosaurs. We think there was a comet that hit the Earth, caused a big cloud of dust to go up into the atmosphere. There may have been some sulfur emissions from volcanic activity and so on. The result of that was it blocked the sun. About 50 or more % of the sun was blocked out for over a year. wiped out the dinosaurs and about 75% of all the other animals on Earth and about 57% of the plant life. So that was the last mass extinction event, but now we're into an era that they're calling the Anthropocene era with anthropogenic causes. What do those terms, Anthropocene era and anthropogenic causes, what does that mean?
Okay, so a few points. Before we get to these terms, let's talk about maybe people say 2 degrees Celsius is not that much. So we experience a lot of more than that in fluctuation of the temperatures. So why we are concerned about this 2 degrees Celsius? The reason is that from the last period of the warming that we had, and from the end of the ice ages, it took the Earth almost 5,000 years to climb in temperature between 4 to 7 degrees Celsius from ice ages out. So that means that a lot of the places we know now, they were covered by ice. From the last warm period that was around 125,000 years ago, our temperature was only 1 degree Celsius higher than today. So now, at that time, the sea levels was 5 to 9 meters higher than today. The UN goal is to keep the sea level rise less than 6 meters, around 5 meters. And if we continue the same way, and all the projections are that we probably will hit the 2 degrees Celsius, a lot of the coastal places that we know they're going to be underwater.
That's going to cause a lot of problems.
That's going to cause a lot of problems. So that's one which is related to the warming of the temperature of the Earth and climate change, as we refer to it. Now, let's go to the Anthropocene. So that means that the rate that the species are extincting is actually comparable to the time that an asteroid hit the Earth. So with the difference that this time asteroid is us, and we are destroying the species.
So anthro means mankind.
Mankind. And we are doing this. And so there are a lot of interesting and devastating numbers out there. For example, almost 50% of the individual animals have been lost within the last century. So that's a very big number. And in a lot of places, almost 80% of the diversity of mammals, for example, have been lost. And these are they have different causes: toxins, overpopulations, humans really going into the wildlife, and climate change. And those are the things that they're contributing to this 6th mass extinction.
Right, and so we're encroaching on the environment of all of the animals, and we're changing the nature of the environment
Yes.
which they live within.
Yes.
And which we live within as well, of course. And then when you get the rising of the sea,
Yes.
That's a recipe for some really bad news.
Yes, and that's, so now we may ask, what will happen if we do not do anything?
Mm-hmm.
So probably we are going to go extinct as well. So there is a perception that we are going to be different than other species, but that's not necessarily true. So if we continue the way we are actually changing the planet, we may see very difficult years ahead in terms of surviving. And that has to do with food resources, that has to do with places that we can live, that has to
fresh
do
water.
Fresh water, that has to do with intensity of the storms. So let's say we had few recent storms, and if now 5 meters higher sea level rise in the coastal lines, that means a lot more intense storms. And all those things, for some countries, those are devastating, and they cannot stand it anymore. And these effects are going to actually become more and more intense.
So we're going to find out just how immortal, which we're not, we're going to find out that we're very mortal.
Yes.
In the coming days. When we talk about alternative energy and sustainable power and so forth, you have talked about the fact that we need to have the influential countries, the wealthy countries, primarily Western Europe, the United States, Canada, Australia, nations like that, that have resources and that do have a lot of influence, they need to take the lead on this. People will say, well, why does America have to take the lead? why can't China take the lead?
Okay.
They're polluting more than we are. And what about India? They're also polluting a lot these days.
Yes.
And what about the Middle East? They're generating more oil than
yeah,
we are.
yeah.
So why aren't they taking the lead on these things? Why do the wealthy, influential countries of the West need to take the lead on this?
So there are a few different reasons. Probably the most important number to look at is if we look at the total emission from pre-industrial age up to today, US is the leading emitter. Even today, US is the top emitter, only after China. So almost 30% of the all CO2 in the atmosphere, they came from US. So that's one reason. And even today, in the total petroleum production, US is the leader. US producing more petroleum, that is the combined oil, gas, and other products. And US has been the leading gas producer in the world for a few years now. And these are recent things. This wasn't the case in 2008. The first year that US actually took the lead over Russia was in 2012 and 2013. And for last 5 years, US has been the leading producer of the total petroleum in the world. So that's one reason that the US is really one of the top emitters. And that is true also about Europe. And European countries also contributed greatly to the total problem or total CO2 emissions that we have in the atmosphere. So that takes us to China. So that is true that today China is the big emitter. One of the main reasons for that is China burns more coal than other sources, and coal is a dirtiest fuel. This was the case for US in the past. Now US has moved on from coal, but China still burns a lot of coal. But China burns those coal and all those energy resources to produce goods. Those goods get consumed in the West. So, and if we look at the per capita, means the amount of CO2 emissions per individual people living in that country, China is far behind all the Western countries, a lot of Western countries. And that takes us to the Middle East. So the CO2 emissions from the Middle Eastern countries, the biggest one are going to be Saudi Arabia and Iran, is less than 2%. Their oil also gets consumed in US, in Europe, and in China. So the problem is really about the wealthy country and rich countries, because they are doing the most of the consumption, and these consumptions or overconsumptions, as we may call them, is the main cause of a lot of these effects that we are seeing.
So what I'm hearing is that the consumption cycle, which involves the West very directly, is the main driver of this at this point in time.
Yes, yeah.
And so we have to go to the break right now, but when we come back from the break, we'll talk about energy return from energy invested. In other words, can these alternative sustainable solutions match the kind of return on investment that we're getting from oil? Stay tuned.
Did you know that you can study climate change, or find fuel in rocks, or even produce synthetic flavors using chemistry? Chemists study chemical reactions and compounds, and how they work in our bodies and the world around us. The opportunities are endless with a degree from Cal State Long Beach.
Welcome back to Talking Points. I'm Dave Kelly, and my guest today is Dr. Hadi Tavassol. And Hadi, when we were talking before the break, we were talking about the consumption cycle and the fact that the Western countries are involved and they're into this very heavily, and all of the other countries are responding to that consumption cycle as part of the world economy. Now, the reason why we're using oil so much is because we have known for the last 75 to 100 years that oil is very efficient, especially that which we can derive from the Middle East, where they have what's called light sweet crude oil, which comes straight up out of the ground, doesn't take a whole lot of refining and a lot of processing, and it's very energy efficient. You can get 30 to 1 or 40 to 1 energy ratio, energy invested for return.
Yes.
So 1 unit of energy to extract it yields 30 to 40 units of energy that can be used. What about the alternative solutions, solar, wind, and so on? Are they going to be able to approach that level of energy efficiency?
So those are two different things.
Mm-hmm.
So when we talk about the energy stored in hydrocarbons, fossil fuels,
Mm-hmm.
that we are talking about their energy density. So these are fuels, so that we extract them out of the underground and we burn them. So now when we talk about renewables, mainly solar, wind, and pump hydro, after we have these plants, we practically do not spend any money to extract the energy. So the energy is free in that sense. So for example, sunlight or the wind is going to give us energy after we have those plants in place. So the investment is going to need to happen in the beginning to just have these solar farms or wind farms or pump hydro plants, and then they're going to give us energy. The difference is that the energy that these renewables provide, they're not stored. So they gotta get consumed right after they're produced. So there is very little storage to it. And we can talk about the storage and what are the consequences of that. But as the energy comes in, for example, on a windy day, pretty much that's no cost to it. Mm-hmm. And if we use the whole of it, we can actually have a very renewable, completely sustainable. And there have been examples. For example, Germany this January got 100% of energy from renewables. Why was that? Because that was the day after New Year's Eve, low consumption day, very windy, and they got 100% of their energy from renewables. Almost 70% came from wind, and the rest of it came from biomass and pump hydro. Mm-hmm. So if the investment and infrastructure is there, we could actually get to those type of numbers. Yeah.
Well, I want to talk about the research that you're doing, and it involves the electrochemical processes that we're talking about. And fuel cells, for example, involve this, where you take hydrogen, which is hydrogen and oxygen, water, and you separate out hydrogen from oxygen, and then you basically take the hydrogen and you run it through a process where you separate the protons from the electrons. The electrons can be used to generate electricity. The protons are attracted through a catalyst to oxygen. It all comes back to form water at the end, and meanwhile you've used those electrons to generate electricity. How does that work in a little bit more detailed fashion without getting into too many details for the audience, because they're not all chemists and engineers? But how does that actually work, and how do we get energy out of that, and how do we start with water and end with water?
So that is one strategy that one can use to store energy. So as I mentioned, fossil fuels, gasoline, is very attractive because of the very high energy density. That means that when you want to fill up your tank, you go to the gas station, it's going to take you only less than 5 minutes. And if you have a big car, you can actually drive for a couple of days if you're traveling. That actually speaks to the high energy density of the fuel. So it turns out hydrogen is it has higher energy density than even gasoline. So it's very dense in energy. So how can we get it? Probably the easiest thing is to split water, right? So if we have water, if we could split water to hydrogen and oxygen, then we are going to have hydrogen. So now, why aren't we doing it in a larger scale? Because it turns out that it's a little bit challenging in terms of chemistry. So it's a challenging reaction to go from water to hydrogen and oxygen. And that needs materials that they're not all of them abundant, and they're not cheap. So now let's assume that we solved that problem and now we have hydrogen. So now we need a device that can extract the energy that we stored in the hydrogen, and that device is called fuel cell. And the fuel cell is going to actually burn hydrogen and give us the energy back, and in the process produce water or give us the water. So that's a sustainable cycle. So you will start from water, you will get hydrogen, and then go back to water. So that's why we call it a sustainable cycle.
In the meanwhile, we're able to extract the energy from the electrons
Yes.
and use that for power.
Exactly. So when you, for example, let's assume that we can use renewable energies, use the energy coming from renewables, split water, get our hydrogen, and when we burn hydrogen back, we can get that energy back. And that's both storage and also very nice fuel to do a lot of different things with it. So that's a strategy behind the renewable, sustainable energy storage in larger scale.
And now you need a catalyst
Yes.
to be able to attract those protons and the hydrogen to the oxygen atoms. And that catalyst usually has to be coated with some nanoparticles. What
Yes.
we've been using in hydrogen fuel cells is platinum powder.
Yes.
And it's very effective, it works very well, but unfortunately platinum is a rare earth mineral. It's quite expensive, it's almost like gold.
Yes.
And so as a result, that adds cost to the process, and it's also not sustainable in that definition
yes,
because it's a rare earth mineral.
Yes.
So we need to move away from using platinum for these very efficient hydrogen fuel cells because they work very well. And also catalytic converters, we were talking about that.
Yes,
When you
yeah.
have to replace a catalytic converter on your car to pass the smog test, it's painful.
Yes.
And it's because largely because of the platinum
Yes,
involved.
yes,
So we need to get away from that. So I know that you're doing research in finding other materials that are not as expensive and are much more abundant than platinum. Can you tell us about that?
Yes. So as I said, there are two parts. So the device that actually converts water to hydrogen, that is called electrolyzer. And it's actually reverse of the fuel cell. So these are reverse reactions. So in both of them, one catalyst is always platinum. That's the state of the art. So now the research actually has evolved a lot that we now have potential candidates that they can actually replace platinum with, that they're not rare earth elements and they're not that expensive. So there are examples, for example, molybdenum is one element, tungsten is another element that base those compounds that we can use. Even more abundant, cobalt, nickel. These are potential things that we can use as a replacement of platinum in electrolyzers and fuel cells. And also, other part of it is the reaction that happens in terms of going from water to oxygen, and again, oxygen to water, that also needs expensive catalyst. And we also been working on that to come up with materials that they are abundant, they're not toxic, and we can actually design them in a way that they are active enough to be economically sound for these devices.
Mm-hmm. And when we talk about these fuel cells, we've been talking about the hydrogen fuel cell, which is what they use for cars,
Yes.
for automobiles, because they're polymer exchange membrane fuel
Yes.
cells, which is all of that process we've been talking about,
Yes, yeah,
separating
yes.
out using a catalytic membrane to
yes.
separate oxygen from hydrogen and so on. But what makes those beneficial is that they're low heat. You can have them in your engine, and the heat that's generated from this process, internal combustion engine burns hot. It burns, fuel. This can operate at 60 degrees Celsius, which is about 140 degrees Fahrenheit.
Yes.
Not very hot. That makes it ideal. However, if you want to have a power plant that's generating enough electricity to power a city, you need something like solid oxide fuel cells, which
Yes.
are much more hot. I mean,
Yes.
those can get up to 1,000 degrees Celsius, which is about 1,800 degrees Fahrenheit. Very hot. But there are some advantages to that and some disadvantages. What
Yes.
are the advantages and disadvantages?
So those are exactly, so if you're talking about the stationary power, probably you want to go with solid oxide fuel cells. The reason is that they're very efficient and they're very good in what they do. And they do not actually need any precious metals. The problem with them is because of the extreme conditions that they work in, very elevated temperatures, the lifetime is actually tends to be shorter. So now when we come to lower temperatures, the low temperature fuel cells and electrolyzers. That means that we can operate in lower temperatures, so that's going to be safe for homes, for cars, for other things. But now we're not going to need some precious metal to actually cover this reduced activity as a result of coming to lower temperatures. And a combination of these two are going to actually be required for different parts or with the different types of application that we need. And this is only, let me mention this, that this is only about hydrogen cycle. And hydrogen is actually a strategy of the larger scale storage. So what do we have in terms of larger scale now? Pretty much nothing. The best we have is pump hydro, which is pumping water uphill and store energy that way. And when you let the water come down, you're going to get your energy back. Those are very efficient, and we can actually use that to store energy.
Just to illustrate that, it's sort of like Niagara Falls, where the water comes down, and as Tesla came up with a way to generate turbine electricity from the water power, you pump it back up, it does it again, and it's
and actually
ongoing.
There are countries that they use pump hydro energy for almost all of their energy. For example, Norway uses probably 90% of their energy from pump hydro. So that's the strategy that we have, but that's limited to the geography, that limits us to a lot of other things. So the larger scale option that we think is going to be most viable is going to be this chemical fuel as form of hydrogen. Now, if we come to a smaller scale, we get to the batteries and lithium-ion batteries. And we are all familiar with lithium-ion batteries because we use them every day in our cell phones, in our laptops, in any electronics that is high-end, it has a lithium-ion battery. Now, the goal is to make it work for transportation. And transportation is very significant because road transportation accounts almost for 67% of the CO2 emissions of the transportation sector, which by itself is 30% of the whole CO2 emission in the US.
We're down to about a minute left, so I want to wrap this up.
Sure.
So lithium-ion batteries, what makes them so great, and are they going to get better?
So that's a question. So probably two-fold or threefold increase in their activity, in their energy density, in their safety is possible. And that's going to have huge effect to the transportation sector because they're already a dominant electric market in US, in Europe, and in China that they're using lithium-ion batteries for transportation.
Very good. Well, I want to thank you for sharing this information with us today. The time just flies so quickly when we're having these kinds of conversations. I'm sure our viewers are well informed now about fuel cells, and they probably didn't know a lot of this information. So thank you again.
Thank you. Thank you for having me.
And thank you for joining us for this edition of Talking Points. Join us again soon for the next episode. Until then, I'm Dave Kelly. Have a nice day.